Anhydrides are molecules that have this functional group outlined here in green. They can be acyclic, as this one drawn here, or they can be cyclic. These are generally water soluble. If you add one equivalent of water to this propanoic anhydride, you get two equivalents of propanoic acid. And so to name the anhydrides, you take the propan and propanoic acid, and you just name it propanoic anhydride. Anhydride kind of literally means without water. So if you take propanoic acid and you remove water, you'll form the anhydride. Now cyclic anhydrides are more stable, and they're harder to react. If we had a molecule such as this, the name of this would be benzene 1,2-dicarboxylic acid. And we placed this into a beaker and heated it. We would drive water off, and I believe this is the one that sublimes, but this guy here is called phthalic anhydride. This is an anhydride. And I don't remember offhand what the temperatures are here, but this might be 150 to 200 degrees Celsius. Okay. And that's one way to form anhydrides, particularly the ones that are cyclic and stable and more feasible for in the lab. Okay. Now, if you look at the textbook, they cite this chemical reaction, right? If you have two equivalents of acetic acid, and this is treated to 100, this is treated at 800 degrees Celsius, you form the acyclic anhydride, and this is reactive. I should point out that the boiling point, if I remember correctly, of acetic acid is about 160 degrees Celsius. So this is done at high temperatures and high pressures, and this is industrial. This is not something we're going to do in the lab. If you wanted to make an anhydride in the lab, and say we wanted to make this one here in green, now this has a total of 4 carbons on the left and 4 carbons on the right, so we say it's symmetrical. This is butanoic anhydride. And if we wanted to make that from butanoic acid, we would not try heating this up to a gazillion degrees Celsius and so on. What we would do is we would treat this with thionyl chloride to get the acid chloride. Okay, and we would call this reactant A. All right. In a different flask, beaker, or whatever, we would take butanoic acid, and we would treat it with sodium hydroxide, and this would make sodium butanate. So this is sodium butanate. Now this we would call reactant B. Okay, and then these two chemicals, if you mixed them together, you would get butanoic anhydride. How does that mechanism work? The mechanism would look like this. Remember again, chlorine is a good leaving group. Your carboxylate is not a very good nucleophile because it's resonance stabilized, but it's sufficiently strong of a nucleophile to attack. You always get this tetrahedral intermediate. We don't directly kick off the chlorine in an SN2 reaction. And then the negative charge from oxygen would swoop in, kick out the chlorine, and you would eliminate to give you butanoic acid. So that's AE for short. So that's how we could make butanoic anhydride if we really had to in the lab. Okay, anhydrides can do pretty much everything that acid chlorides do. They're reactive, they're water sensitive, and water they're not very stable, so there's a chart in your Klein textbook on the bottom of page 1011 that shows all of the different chemical reactions you can do with this. So let's take butanoic anhydride as our example here. Let's place this in the middle. Okay, and if we treat this with water, we can form two equivalents of the butanoic acid. We can treat this with an alcohol. Let's treat it with ethanol. Ethanol. And what we'll get is an ethyl ester. And we'll get one equivalent of the ester, which is a leaving group. Okay, and I'll show this mechanism here in a bit. We could add excess or two equivalents of ammonia to this. And this will make an amine. And it will kick off this leaving group. We can add primary or secondary amines to this as well. So I could add ethylamine to this, and I'll get the N-ethylbutanamide. I could add dimethylamine to this, and what I can get is the N,N-dimethylbutanamide. I can also treat this with various reducing agents. I can treat this with lithium aluminum hydride. And this will give me two equivalents of an alcohol, butanol. I could treat it with a monohydride reducing agent. Lithium triterbutoxyaluminum hydride. And this would give me, ideally if things work well, an aldehyde. Okay, so it doesn't reduce it all the way down to an alcohol. It stops at the aldehyde stage. And I can treat this with cuprates. Okay, we'll talk about cuprates in a bit. Okay, so these are all the different reactions that anhydrides can undergo. Now I will be discussing for you how aspirin is made. Aspirin is made from this. The name of this is salicylic acid. Okay, and this is a phenol functional group, and we treat this with acetic anhydride. And this will create the ester at this position here. And this is aspirin. Okay, fever reducer and all that. So how does the mechanism work? I'll show you that in green here. And so this is going to be our nucleophile. And that oxygen is going to attack the carbonyl carbon. Okay. And we could do one of two things at this stage. We could kick out our acetate. And acetate's the leaving group. Okay, this highlighted section here is the leaving group. Just like chlorine is a good leaving group in acid chlorides. And so what we get here after this elimination step is this intermediate. And we have acetate, floating around over there. And so the acetate can deprotonate here. And that gives us an equivalent of aspirin and one equivalent of acetic acid. And this is one of the reasons why when you make aspirin, you smell that vinegar flavor smell. Okay. So let's look at the mechanism here. That's AED. Okay. And that's how salicylic acid becomes acetyl salicylic acid or aspirin.